In this lesson, we're going to take a look at vector projections. Vector projection is kind of an application of vectors. Here what we're going to take a look at is what happens when we perform work in one direction, but the object that's being moved happens to move in another direction. Its displacement is different than the direction of the force. And so take a look at this example here we have on the page. We have a wagon full of books, and we want to tow this wagon. Well, for towing the wagon, we're pulling up on the handle and at a certain amount of force, but the wagon itself isn't moving diagonally up, it's moving forwards in a horizontal direction. So some of the work that we're doing is actually being wasted. And at times it might be useful to know how much work we're doing and how much effect it's actually having. So that's the idea behind a vector projection. To actually calculate a vector projection, what we're going to do is we're going to drop a vector onto another vector. So we'll take a look at this first one here, this is the picture. If we look at the direction that we're pulling in, and we drop that from the point downwards in the direction we're pulling, we form a triangle, a nice right angle triangle. And the distance from where the force started to where it was dropped would be called our vector projection. Before we start with the math, a little bit of notation for you. When we project A onto B, that is when we drop A onto B, we use this downward pointing arrow, A onto B. And from our previous diagram, the same diagram we had before, here's where the wagon would be right here. We can think of this as two vectors, geometric vectors with an angle between them. If we were to project A onto B, that is drop A onto B, the distance between O and N, O and the scalar distance, would be a projection of A onto B. And the good news is it's a nice right angle triangle, which means you can use SOHCAHTOA to figure out how long that vector actually happens to be, or that scalar distance happens to be, using the angle and the hypotenuse. I just want to point out before we move on here that A onto B is different than B onto A. If I want to drop B onto A, I'd start at the point of B and drop it onto A at a right angle. In order to do that, I'd actually have to extend A, so I could drop it onto A. And then this distance right here would be my distance of B dropped onto A. And notice those two things are different sizes, right? A on B and B on A are not the same size. And so just because we know one, we do not know the other. Okay, so I want to do the math now. How do we do the math to find the projection of A onto B? Well, first of all, we'll talk about the scalar length, the size of that projection. To do it, we're going to use some trigonometry. We're going to use some SOHCAHTOA. If I take the cos of the angle between the two vectors, the cos will be the adjacent, which is my vector projection. That's the A. And the hypotenuse, the H, is the vector A. So I can say the cos of the angle is my vector projection over A. Or if we cross multiply that, our vector projection, ON, which is just A onto B, that's all that is equal to A cos theta. Notice we have two scalar values. And because we have two scalar values, our answer is going to be a scalar answer. Now that works great with geometric vectors because we know the angle between them. But what if we don't? Well, then we can use our dot product. So if we go back to our dot product idea, A dot B is A times B times cos theta. And if I just rearrange that slightly, just move the B and the A swap places there, we have the exact same formula, just a slightly different order. And if we were to divide out the B part, it would look like this. A dot B over B equals A cos theta, which is what we set up here, the dot product, or the vector projection, right? So we can replace A cos theta with ON, which is the same thing as saying A projected onto B. Right, so there's how we developed a formula sort of for a scalar projection of A onto B. Notice that the B is on the bottom, and it's the second letter. And so if I wanted to do B onto A, it'd be the same dot product, but it would be over A. Okay, so let's try one. So we're looking at some algebraic vectors here, component vectors. I've got V and U. I want to sketch and determine U onto V and V onto U. So we'll start with our drawing. V is 2, 3. So 2, 3, I'll call that about there. That's v, 2, 3. And u is 3, 0. So u would be about here, right? U, 3, 0. And I want to drop v onto u. We'll do that one first. So actually, we'll do u onto v first. So from u onto v at a right angle. So if I drop the line at a right angle, the distance from here back to the beginning would be u onto v. And how do we find that? Well, the formula we just developed. So I take the dot product of the two things, u dot v over the magnitude of v. Algebraic vectors, you can find dot product pretty quick. 2 times 3 is 6. 3 times 0 is 0 over the magnitude of 2 squared plus 3 squared. So we get 6 over root 13. And that's what u onto v would look like. If we did v onto u, so from the point of v down onto u, this distance here would be v onto u. And we can find that value, v onto u, by doing our dot product again, which we just found out was 6, over, because it's v is the second one, the square root of the component of v. So, I'm sorry, the square root of u. Sorry, 3 squared plus 0 squared. So 6 over root 9, which is 6 over 3, which is 2. Okay, so different values for sure. And if you look at the picture, they look like different lengths also. And that's why we find scalar projections. Now, we also want to be able to deal with vector projections. So the idea of a vector projection is that we take a unit vector in the direction of your projection and use that to measure the vector projection. So if we go back to unit vectors for just a second, that was 1 over x times x. Well, that's kind of what we're doing here. Okay, when I do a vector projection of a onto b, I'm taking my 1 over part, which is right here, and I'm going to multiply that with a scalar value, which is right here. So this is a scalar, this is my unit vector. If I multiply those two things together, I end up with this expression, a dot b over b squared in the direction of b. And that's nothing wrong with using that one, but sometimes we have a different version of it. We could also call it a dot b over b dot b in the direction of b. Because remember, b squared, we talked about the other day, was b dot b. Those being the same thing. So it's just two different versions of the same formula. So using the same values we did a second ago, if I want to find the vector projection of u onto v, okay, my formula is u dot v over v dot v. I'm using the second formula here, and the direction of v. So u dot v would be 6 plus 0, v dot itself is 4 plus 9, and the direction of v is 2, 3. Let's simplify, we get 6 over 13 times 2, 3. And if we expand that just to make life a little bit easier, we get 12 over 13 and 18 over 13 for our components. Here's the vector projection. So once you know the scalar projection, you can find the vector projection pretty quickly. And if I do the v projected onto u1, okay, same idea. I do v dot u, which we already know is 6, over u dot itself. So 3 times 3 is 9, 0 times 0 is 0, and the direction of u, 3, 0. I've got 6/9 times 3, 0, which is like 2/3 times 3, 0, which is 2, 0. And there's our vector projection. Okay, some applications. How can we actually work with this stuff? So let's take a look at example number 3. We got two vectors, with magnitudes. Magnitude m is 8 and n is 11, and we know there's an angle with 135 between them. We want to determine m onto n, and we want to illustrate that. So first thing we need to do is draw this picture. We got m, and we got n, and n's a little bit longer. And we know they make an angle of 135. We know it's always tail to tail when we say angle between them. I want to drop m onto n. So I need to start at the point of m and drop it onto n at a 90. Well, this is one of those situations where we need to extend our line so we can hit it at 90, because right now it's not possible. If we extend the line and drop it down, we can end up with a 90 right here. So m onto n, from here to here, m onto n. And because it doesn't have the scalar signs, we want the vector signs, we can find the vector projections. How's that going to work? M onto n. Well, what's our formula? Our formula we just developed was m dot n over n dot itself, in the direction of n. That was great when we had those algebraic vectors, right? We can do dot products really easy with components, but we don't have components anymore. We now have the geometric version again. So let's go back to the dot product idea. What is m dot n? Well, that's the magnitude of m times the magnitude of n times the cos of the angle between them. And n dot itself, well, that also means n squared. The direction of n, well, we were allowed to draw this in whatever we wanted to. It's a geometric vector, so we don't really have a direction per se. So we're going to use the letter n for that. Now, what do we know? We know m is 8. We know n is 11. We know the angle between them. Well, it was 135. Okay, so we can put that angle on there. And we know the size of n was 11, and we're going to square that, all in the direction of n. Okay, we can put that all in our calculator all at one time. If we do it right, it should come out to negative 0.514. And again, we don't have a direction for n, so it has an n vector attached to it. Okay. So sort of a simple application of how we can use these vector projections. If we talk about R3, because we always want to talk about R2, R3, the properties that work in R2 always work in R3. They're basically the same properties. So if I wanted to find A onto B, vector and scalar, I can do both. Three-dimensional is just worry about three components. So A onto B, we'll start with the scalar one first. Scalar would be A dot B over the magnitude of B, right? That's our formula. So A dot B is negative 8 minus 2 plus 6 over the square root of 2 squared plus negative 2 squared plus 2 squared, which gives us negative 4 over root 12. And there's our scalar. If I want to do the vector version of that, A onto B, and just go back to the formula for a second, we can notice the shortcut here. A dot B over B dot B, direction of B. Well, we've already figured out some of these parts and pieces, right? We've already figured out that A dot B was negative 4. B dot B is just the magnitude of B squared. We know the magnitude of B is root 12, so if we square that, we get root 12 squared. And the direction of B we know is 2, negative 2, and 2. So we end up with negative 4 twelfths times 2, negative 2, and 2. And if we simplify that, negative 1 third, 2, negative 2, and 2. And if we expand those brackets, we end up with negative 2 thirds, 2 thirds, and negative 2 thirds. And there's your vector projection.